Okay, so today guys, we're going to review our second test, which was just on the applications of calculus. So we did that from about week 7 to week 11 of term 1. And what we'll do, we'll flick through the content. So on SAT 2, applications of calculus, so we'll just read through the content to refresh our minds on this stuff together, and then we'll answer the questions over leaf together. There should be enough space there. So the first thing we talk about is tangents and normals. So if you remember, the textbook only goes through tangents, but we had some extra normal questions as well because it explores both tangents and normals. And so a tangent is just a line parallel to the curve. And we looked at really three different processes of finding tangents. Basically, it starts with finding the slope, finding the point of contact, and then finding a line that goes through those. Very good. Then on to 3b, we look at when is a function increasing and decreasing. So if we have f of x, we know that f dash of x describes the rate of change of f of x. And so, if the rate of change is positive, it means the function is increasing. If the rate of change is negative, it means the function is decreasing. So we use the sign diagram of f dash of x to tell us when is a function increasing and decreasing. That's what we're doing in exercise 3b. In 3c, we extend that because we go from increasing to decreasing, gives us a local max, and from decreasing to increasing gives us a local min, and from increasing to horizontal to increasing gives us a stationary point of inflection. All right, so the sign diagram of f dash of x having these properties, all right, it tells us about the original function. We would be, increasing and then decreasing. Positive slope and negative slope results in a local max. So all that's exhibited along there for 3c. Then on 3d, we looked at what the second derivative tells us. Okay, so the second derivative, if we draw the sign diagram of the second derivative and the sign diagram changes sign, then we have a point of inflection. That's when it changes shape, right? From being concave down to concave up and vice versa. A point of inflection is the location where it changes. Stationary point of inflection here, because we have concave down and then concave up. Very good. So that's like all about the shape of a function. Then on to 3e, we looked at kinematics. So we're looking at s of t being displacement, v of t is the rate of change of displacement. We have some points there about velocity, acceleration, and speed. 3f is about rates of change, and so that's if we have a function, f dash of x describes the rate of change of the function. So it could be the height of a tree, the volume of water in a tank, and h dash of t describes the rate at which the tree grows, v dash of t describes the rate at which the volume changes. So that's all in exercise 3f. And then in 3g, optimization is where we're looking at the optimal solution using calculus techniques. So we know we have some function that's describing some relationship. F dash of x can reveal to us the maximum and minimum solutions to that relationship. So let's get straight in then. So just on the page opposite our summary here, we have equations of tangents and normals. And our first question is find the equation of the tangent 2. And we have 2 on x squared at minus 1, 2. So y equals 2 on x squared at, and we're given the coordinate, we're given the point of contact already. X is minus 1 and the y value is 2. So we need two things, right? We need the point of contact, which we've got, and then we need the slope. And in order to find the slope at that point, we're going to find the slope function. Firstly, we'll express y in a manner ready to differentiate. And then we'll differentiate. Alright, and then we're going to put this x value into here. So we'll have when x is minus 1, the derivative is minus 4, minus 1 to the minus 3. Now what this technically means, I suppose, is minus 4 on top of minus 1 to the 3, which is minus 4 on minus 1, which is positive 4. All right, now you might remember all of that we can get from our calculator, that we could graph this function and we could g-solve when x is minus 1, it's going to tell us the y value and the value of the slope. Okay, as long as we have the derivative mode turned on our calculator, it can tell us both of those. And then all we're doing is we're finding the equation of a line with these properties. It has a slope of 4, and it passes through minus 1, 2. So we have when x is minus 1, y is 2. Very good. Okay, so when we did the test, I think normally the first question is about tangents and normals as well. And then we have a question that reflects on the exercises 3B, 3C, and 3D all together. All right, because that's a skill we certainly can assess all together, because we're taking a function and we're trying to discover its properties using calculus techniques. So the function that we're given in our example here is x to the 3, take away 3x squared. And we are asked, find when f of x is increasing and decreasing. Now, of course, one thing we could do is look at the graph and g-solve all of these properties, right? But we're using calculus techniques. So that means we're going to first differentiate it. And then we're going to draw its sign diagram. All right, now I'm going to make a manual argument for drawing a sign diagram just to recap those algebra skills again. But from here we could graph that in our calculator and get the sign diagram from the calculator, right? So what we would do if we want to solve when this equals 0, if we want to solve a sign diagram, we would factorize 3x. We can f of x take 2, and this gives us the solutions x is 0 or x is 2. So for the sign diagram, 0 and 2. It's a quadratic that has a positive a value, which means it's opening upwards. So we have positive, negative, positive. So that's the sign diagram of f dash of x. And we can now answer part A. All right, so for part A, we would say increasing. Now the original function is going to be increasing when the derivative function is positive. And it's going to be decreasing when the derivative function is negative. So we would say that values of x less than 0 and greater than 2. Make sure you get your arrows around the right way. If you want to practice that skill, I've got some good tips on how to make sure we know which way they're going. Okay, so that's increasing and decreasing, that's part A. And then part B says, what about the stationary points? All right, well, stationary point is when the slope is 0. The slope is 0 at these 2 points, right? Because they're the roots on the derivative function. If it's a root on the derivative function, it means that's where the derivative function touches or crosses the x-axis. It means that the slope is 0 at these points. So we can see it's a local max because we're increasing and decreasing. All right, we have a local max at 0. And then we want the corresponding y value. We want the y value from the original function. All right, so we put x is 0 in, we get the y value of 0. And then we have a local min because we're decreasing and increasing at 2. X is 2. And then the y value is going to be what? 8 take away 12, which will be minus 4. Those are our 2 stationary points. Very good. Then part C is saying, when is it concave up and concave down? And part D is asking about the points of inflection. Now for that we'll need the second derivative. So we've got f dash of x is this, 3x squared takes 6x, which means f dash dash of x will be 6x take 6. And to draw the sine diagram of f dash dash of x, it's going to be the equation of a line. Has a root of 1. It's a line that has positive slope. So that means it's going up like this. So that's what our sine diagram will look like for the second derivative function. Now again, we can make the manual argument, but we can just go straight from our calculator to there. Remember, we can use our calculator to graph the first derivative and the second derivative. Now what this tells us, okay, because the sine diagram changes sign, we have a point of inflection there. That means here it's concave up, here it's concave down. Okay, so we would say concave up for x is larger than 1, concave down for x is less than 1, and we have, it's not, we have to stipulate it's, so that's part C. For part D, we need to stipulate the nature, always the nature of a turning point. So like here, these are stationary points. We wouldn't say that they're, you know, stationary point and stationary point. We have to say what kind of stationary point they are. Similarly, here we need to say what kind of point of inflection it is. We either have stationary or non-stationary. Now, a stationary point of inflection will also occur on this sine diagram. Now, this point of inflection does not occur on this sine diagram, which means it is a non-stationary point of inflection. X is 1 and the y value will be 3 take 6 minus 3. Alright, now all of those features we can get from the graph really encourages you to use the calculator to support you. Alright, let's move on to 3E unless we've got any questions. So, in 3E, we have kinematics. We have a particle moves in a straight line, and this is its displacement function. We have S of t is 12t, take 2t, the power of 3, take 1. Part A, find v of t and a of t functions for the particle's motion. Alright, so v of t is the derivative of s of t, so we differentiate this. That would be 6, 3, 12 takes 6t squared. And a of t is the derivative of v of t. A of t is the rate at which velocity changes, so that would be minus 12t. Okay, part B says find the initial conditions and interpret their meaning. This means what's the initial displacement, what's the initial velocity, and what's the initial acceleration. And so we'll have, when we put the number 0 into this equation, we'll have minus 1. And the units that we've got here are centimetres. So initially it is 1 centimetre to the left of the point of origin. When we put 0 in here, we'll have 12 centimetres per second. That's how fast it's moving. It's moving towards the right because it has positive velocity. And the acceleration is negative 12 centimetres per second squared, which means it's accelerating in the negative direction. Okay, so that's part B. As far as interpreting their meaning goes, often in the textbook they'll write a sentence about what all that means. The acceleration should be 0. Oh, sorry. Yeah, when you put the number 0 in here, minus 12 times 0, that's 0. Thank you. That means the speed is not changing initially. Thank you, Ade. Alright. Okay, part C. Find the times and positions when the particle reverses direction. So what we're going to need to do here is draw the sine diagram of the velocity function. So if we consider the velocity function, this is it here. We could just go straight to drawing it using our calculator, but let's make the manual argument again. Its roots are going to occur when it's equal to 0. So we're solving this equation. T squared is 2, and we'll get t is plus root 2 or negative root 2. So we have 2 roots, right? Now remember, with kinematics, we only consider positive values of time, so we're not really interested in this one. I am going to sketch it for the sake of the sign diagram, but then I will erase it. So what we have is, when we're doing kinematics, we consider positive values of time, right? That's where we're starting. And the roots of this quadratic are at positive root 2 and negative root 2. Here they are. And this quadratic has a negative a value. Okay, the coefficient of the t squared component is negative, which means it's opening downwards. So it would have this shape, which means it's going to be positive here and then negative here. We're not interested in this part of it, are we? All right, so that's the v of t function. And so in order to answer the question, it says determine the time and position when it changes direction. Okay, so what we'll say is that it changes direction. It changes direction because it changes sign. It's moving to the right and then moving to the left. All right, so answer to part C. Changes direction at t equals root 2, and then we want to know the position, and so what we would do is we put the number root 2 into the displacement function. Now when I'm doing this, like what I'll do is I'm going to leave that for now, and I'm just going to evaluate all of this stuff in my calculator right at the end. I'm just getting it all ready, and I just smash it all in my calculator at the same time. Really up to you how you do it. That's just how I like to do it. Okay, then for part D we have, at what time is the particle's speed increasing and its velocity increasing? So I'll just take you to, in kinematics, we have, towards the bottom we have two dot points. Well, we have an object changes direction if its sign changes in the sign diagram for velocity. Speed of an object is the magnitude of its velocity. If v of t and a of t have the same sign, then speed is increasing. If they have opposite signs, then speed is decreasing. Okay, so in order to find when speed is increasing, we need to draw the sign diagram of the acceleration function. I'm going to draw it immediately beneath it. This is our acceleration function, and it's going to have a root of 0. All right, it's the equation of a line. That, what's the value that's going to make it equal 0? T is 0, and it has negative slope, which means it's going like this. Going down, it's always negative. So that's our a of t function. And so speed is going to increase when both of these have the same sign. And what we can see is that they're both negative for values of time larger than root 2. All right, so in order to answer D part 1, we would say speed increasing t is larger than root 2. So what we can see, they're both negative for values of time larger than root 2. Okay, what about when is the velocity increasing? Now velocity will increase if acceleration is positive. So when is the acceleration positive? Never. All right, so in order to answer part 2, never increasing. And if we wanted to give a mathematical justification, we could say something like a of t is less than 0 for t's for positive values of t. All right. Part E says draw a motion diagram of the particle. So if we want to draw a motion diagram, what we're going to want to know is we're going to know where does it start, where does it change direction, and where does it finish. And we're not given a constraint on how long to finish it for. And so what we might even just draw is an arrow to indicate which direction it's going in. And this is the stage where I would evaluate this because I need it in order to draw the motion diagram. We've already evaluated this one. So I'll just evaluate that quickly in my calculator. Root 2. So we will have 12 root 2. Take 2 root 2 minus 1 plus 8 root 2, I'm just going to convert it to a decimal. We get 10.313. Alright, now one thing we could do is we could find a later value of time. So root 2, that's about 1.7, right? So we could find a value of time later than that, like times 2, 3 or 4 if we wanted to. But all I'm going to do is draw an arrow to indicate which direction it's travelling in. So as far as our motion diagram goes, it's an axis, and on the axis we're going to draw the important points. Here's the point of origin, and here's where it starts, isn't it? We're told that it starts initially when time is 0, it has a displacement of minus 1. And then I might put like 11 here and 10 here, and it's about 10.3 when it changes direction. So I'll just elevate that point a bit, about there. So it comes to here, and it changes direction after root 2 seconds, which means it's no longer moving to the right, it starts moving to the left. And it will move to the left for the rest of its duration, because we can see velocity is negative for the rest of the values of time from a sine diagram. So that's fine. If we wanted to, calculate total distance travelled, we could find some points and add them together, but that's what it's doing. And so we can see initially it's at this location. It's moving at 12 centimetres per second to the right, so it's moving in this direction, and then it starts moving to the left because it has a negative velocity for the remainder of its duration. And it's going to speed up in the left direction. It's going to get faster and faster in that direction because we showed that speed is increasing for values of time greater than root 2. Very good. So kinematics, any questions about that one? So that was probably a more difficult kinematics question. Let's move on to 3F where we have rates of change. Alright, and here we have the height of Pinus radiata. So local pine trees is H equals 20, take 97.5 on top of T plus 5. Where T is the number of years after the tree was planted from the seedling. Part A, how high was the tree when it was planted? So what this means is it wants us to find H of 0. Now this is one again where we'll use our calculator, and I might just do all of these calculations in a moment. We might be able to just look at our graph and just get more from it. Part B part 1 says find the height of the tree after 4 years, 8 years and 12 years. So this means it wants us to find H of 4, H of 8 and H of 12. Part C says find the rate at which the tree is growing after 0, 5 and 10. Now the rate means it wants us to find H dash of 0, H dash of 5 and H dash of 10. And this is where our calculator is incredibly useful, right? Because it's just a matter of G solving from the derivative function. And then part D is arguing show that dH on dt is positive for all values of t. So we might do that part in a moment when we go ahead to find the derivative. For now, let's use our calculator. So what I'm going to do, I'm going to graph this function. I'd like you guys to follow along as well to make sure your calculator is the right setting. And we're just going to make sure that we can trace along these values of time to determine the y value and the slope value. So in graph 20, take 97.5. And we're only interested in positive values of time, right? Because it's the height of a tree. And what I'm going to do is I'm going to trace along it. So I press F1 to trace along it, and it pops up with my x value, my y value, and my dy and dx value. Now we're certainly interested in its initial point, so we'll type in when x is 0. And I've got the corresponding y value is 0.5. We'll give it a unit. Now we're told the height in the tree is in meters. So initially it's 0.5 meters high. All right, and the dy and dx value there is 3.9 meters per, and then the time period is year. All right, now I'll get.
How do you get the
does it not say it above the y value for you? No, I'll come turn on the calculator setting. Everyone else got it? Yep. So if you press shift menu, and then just scroll down to it, says the root meter. So I reckon, oh, it's because you G-solve. Press trace. Yeah. So that's a bit annoying, it doesn't work with your G-solve. Alright, so let's get the rest of these. So if we go for 4, we'll have 9.1, 6 recurring meters. We go for 8, 12.5 meters. If we go for 12, after 12 years, it is 14.3 meters 2. Alright, then we want the rates of change. So we go to 5, the rate of change is 1 meter per year basically. And then after 10 years, the rate of change is 40 centimetres per year. Slows down a bit. Very good. Okay, so that's just using our calculator to determine the rate of change. But let's have a go at answering part D using our calculus techniques. So we know that this is the h function. 20 take 97.5 times t plus 5 minus 1. And we're going to differentiate. We're going to find dh on dt. Alright, we can do so in one step using the chain rule. Derivative of 20 is 0. The minus 97.5 can stay up front. And then we're just differentiating this component using the chain rule. We have a function to the power of n. So n, f of x, n take 1, f dash of x. Okay, derivative of this. So that's what it is. We'll just simplify that. Here, minus 97.5 times minus 1 is positive 97.5, and the t plus 5 squared at the bottom. Alright, that's our dh on dt function. Show that dh on dt is positive for all positive values of time. So all we're going to show here is that we're going to break it down into its components. Alright? And so its components are the top and the bottom. And so what we would say is we'd say t plus 5, t plus 5 squared is going to be positive for all t larger than 0. Alright, that even if you put, doesn't matter what value of time you put in there, we get 0, 1, 2, 3, 4, 5, 6. Alright, we're going to have 0 plus 5, or 1 plus 5, or 2 plus 5, and then we're squaring it. This part is always going to be positive. Okay? So, because t plus 5 squared is positive, and 97.5 is positive, therefore 97.5, a positive number, divided by another positive number, will always be positive for all t, all positive values of t. So, 3G, optimization. Alright, so now we're into the fun problem solving stuff. We have a 2 litre box, has a square base and an open top, and its dimensions are labelled. Explain why. So here's our box here. And the base is x, and the sides are y. Alright, and so its volume is x times y, right? What would you say? Length times width times height, which is x squared y. And this is equal to 2 litres, which is also 2,000 centimetres cubed, right? And so then if we divide both sides by x squared, we would have y equals 2,000 on x squared. So we have a way of presenting y. Part B, show that the surface area of the box. So that means the base plus the 4 walls, right? So we can call that the surface area function. It's equal to the base plus 4 walls. So the base is going to be x times x, which is x squared. And the walls are going to be 4 times x times y. Alright, so each wall has an area of x times y, and there's 4 walls on the box. However, here we have 2 variables. We want to express it as a single variable of x. So we're going to substitute this in here, this expression for y. So we would have x squared plus 4x times 2000 on x squared, which simplifies to 8000 on x. So that's our surface area function in terms of x. Part C, find the dimensions of the box which minimize its surface area. So what we would do is we're going to differentiate the surface area function. So first we'll express it in a way ready for us to differentiate it. Then we can differentiate it. And now we want to graph we want to draw the derivative of this function or find its root. Okay, so if we want to find the root of this function, we're going to make it equal to 0. And what we basically have here is we have 2x take 8000 on x squared times both sides by x squared. We always want to get rid of denominators. And then we're just solving away. Cube root 4000, just under 15, I reckon. Over 15, 15.87. Alright, so that's the value of x. It says find the dimensions of the box which minimize its surface area. So that's the value of x. Now, if we want dimensions, we want to express it like this, right? X times y. And so if we have x is 15.87, we can find the y value. Oop, 15.87 squared. We'll evaluate that. We've got 7.94 for the y value. So to answer the question, make sure we answer the question. Alright, now that gives us the minimum surface area. Now, what we also need to do here, it's not really enough just to find the what we've found. If we've found the optimal solution, but we need to communicate that with a sign diagram. Again, x is only going to have positive values because you can't have a negative length. And there's only one root, we've established that it's 15.87. And it's a minimum solution, so we can really reverse engineer this. So that means it's going from negative to positive. And this is the sign diagram of SA dash. And all we need is that accompanying our mathematics here to demonstrate that that's the minimum solution. All right, we can get that from our graphics calculator as well. And then part D says find the minimum surface area. And all that's going to involve is putting the number 15.87 into the surface area function. All right, so it's surface area when x is 15.87. And we'll have 15.87 squared plus 8,000 on top of 15.87. I've got 756 centimeters squared is the minimum surface area. Tremendous. So that's a good summary of applications of calculus. That was a nice long one.